Hello everyone, we present token fusion, bridging the gap between token pruning and token merging. This paper focuses on accelerating vision transformers, which have become a prevalent backbone in image-related tasks like classification and image generation. As the application of vision transformers expands to mobile devices, the demand for their faster performance becomes increasingly important. Our approach to speeding up vision transformers revolves around reducing the number of tokens in the model. There are two main methodologies for doing so. Token pruning. This method involves eliminating less important tokens. It relies on specific criteria to gauge and decide which tokens are less critical and can be dropped. Token merging. This technique highlighted in the paper Token Merging focuses on amalgamating similar tokens. The rationale behind this is to consolidate tokens while retaining maximum information. To demonstrate the distinction between token pruning and token merging, let's consider an example using a 4x4 grid of tokens. In token merging, the grid's tokens are divided into two groups. This division is based on selecting the top R most similar pairs of tokens. After selecting the tokens, we merge the chosen source tokens into their corresponding destination tokens using a method of weighted averaging. By combining the most similar tokens, we effectively reduce the total number of tokens. As a result, the subsequent operation of the vision transformer becomes more efficient and requires less computation power. Contrastingly, token pruning can be visualized as simply removing certain source tokens without integrating them into destination tokens through averaging. In this process, although the resulting number of tokens is the same, the destination tokens remain unaltered. In this paper, we pose two questions. Under what circumstances is pruning more effective than merging? Is it feasible to integrate both pruning and merging into a single and unified algorithm? Given that token reduction techniques often balance efficiency against performance, our paper's objective is to enhance efficiency while minimizing the impact on performance. To achieve this goal, we introduce token fusion. We begin by analyzing how pruning or merging affects vision transformer models. Consider x1 and x2 as arbitrary tokens. Let f represent a function within the VIT model, which could be an MLP or attention modules. Our aim is to closely examine the behavior of the function f of x. In the case of pruning, when we remove x2, we are essentially discarding f of x2 as well. However, for merging, when we combine x1 and x2, the average token becomes the input for the nonlinear function f. A critical question arises: what if f of average significantly deviates from the f value of each individual x? This could potentially lead to a shift in the distribution. More specifically, let's consider f as the actual MLP for a pre-trained vision transformer. For easier visualization, we sandwich the MLP layer with linear layers that project the feature into two dimensions. Our goal is to graphically represent the path of linear interpolation between x1 and x2 and observe how it transforms under the function f. For MLP layers in the early blocks of vision transformers, the interpolation path is markedly nonlinear. This is observed when the midpoint of x1 and x2, once transformed by f, deviates significantly from the midpoint between f of x and f of x2. In contrast, for MLP layers derived from the later blocks of vision transformers, the degree of nonlinearity diminishes. Despite f being a nonlinear function, the interpolation path between x1 and x2 tends to be closer to to a straight line. This characteristic is advantageous for average merging as it leads to less deviation in subsequent operations. To measure this property, we use a metric called functional linearity and chart its value for each block in the vision transformer. A higher value of this metric indicates greater linearity in the function. Small linearity region is observed in the early blocks. Lack of linearity is not conducive to average merging. Therefore, employing pruning in these early stages is more advantageous. We also observe a relatively large degree of linearity in the latter blocks of the vision transformer. In these regions, it is beneficial to utilize average merging. The final algorithm we propose is a combination approach. We employ pruned merging in the early layers of the vision transformer and switch to average merging in the latter layers. Additionally, we substitute the average merging operation with a norm-adjusted average merging, so-called MLERB operation. This change addresses the issue of diminishing feature norm that often occurs when average merging is performed. The performance impact of our approach on ImageNet classification is illustrated on the left, showcasing two different sizes of vision transformer models. This second row demonstrates the effect of the token fusion. Third row demonstrates the additional benefit when replacing average merging with MLERB merging. Token fusion is able to be used also without additional training for its convenience, and it can be used with batch dimension during inference for more efficient usage. We can also apply token fusion and diffusion models. The top row shows the images generated with full tokens. The second row shows the previous method token merge result. Note that some contents change from the full model result. The last row shows the token fusion result and is able to preserve the overall structure better. For details, please check out our paper and poster. Thank you.